All right, let's dive into one of the biggest, most fundamental challenges in all of chemistry. See, in the lab, we can weigh things, right? We can measure out grams of some powder or liquid, but the real action, the chemical reactions themselves, they happen between individual atoms and molecules. So the question is, how do you connect the stuff you can weigh to the stuff you can't even see? Well, it all comes down to one of the most powerful ideas in chemistry. So here's the big question, right? How do you count things that are invisibly small? It's kind of like trying to bake a cake, but instead of the recipe calling for a cup of flour, it asks for exactly 500 billion grains of flour. It sounds completely impossible, but chemists came up with an absolutely brilliant solution. And this is the disconnect we're talking about. On the one hand, you've got your lab scale, which measures mass in grams. But on the other hand, the chemistry itself, the reactions, they depend on a specific count of atoms and molecules. We need some kind of bridge to get from mass over to count. So to build that bridge, we're going to assemble a kind of chemist's toolkit. By the time we're done here, you're going to have a complete set of tools that lets you solve some really cool molecular mysteries. Okay, first thing in our toolkit, what I like to call chemistry's secret number. This thing is the master key that unlocks this entire process. And that key? It's called the mole. Seriously, that's it. And a mole is just a word. It's a word that stands for a very specific, very large quantity of things. It is the number chemists use for counting. And what a number it is. 6.022 times 10 to the 23rd. This is Avogadro's number, and it is so mind-bogglingly huge that if you had a mold of pennies, you could give every single person on Earth $1 trillion. This number, this is the heart of our entire toolkit. Look, the absolute easiest way to wrap your head around this is with an idea you already use every day. We all know the word dozen is just a shortcut for saying 12. Well, a mole is the exact same thing. It's just a chemist's shortcut for saying that ridiculously huge number of atoms. So how does this actually work? Let's say we weigh out 32 grams of copper. To turn that weight into an atom count, we just need one more piece of the puzzle. Copper's molar mass, which you can find right on the periodic table. Think of it as how much 1 mole of copper weighs. So we take our 32 grams, we divide by that molar mass, and that tells us how many moles we have. Then we just multiply that by our master key, Avogadro's number, to get the actual atom count. And boom, we just counted over 300 sextillion atoms by using a simple scale. Pretty cool, huh? Okay, tool number 2 is all about reading recipes. We're going to see how chemical formulas aren't just letters and numbers. They're actually incredibly powerful conversion factors. Let's take something simple, like water, H2O. The formula is a recipe, right? It tells you that for every 1 oxygen atom, you need 2 hydrogen atoms. But here's what's so amazing. That recipe works on the moles scale, too. So 1 mole of water molecules has 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The formula gives you a perfect mole-to-mole ratio you can use for anything. Our third tool is all about identity. It's like finding a compound's unique fingerprint, and we do that by looking at its mass composition. This fingerprint is called mass percent composition, and all it is the percentage of a compound's total weight that comes from each element inside it. This is a super important piece of data, especially when you're trying to figure out what an unknown substance is. Now, if we look at the mass of water, something really interesting pops out. Even though there are 2 hydrogen atoms for every 1 oxygen, oxygen atoms are so much heavier that they actually make up almost 89% of water's total mass. That specific 89 to 11% split, that's a unique fingerprint for water. No other compound has it. All right, our toolkit is officially complete. We've got the mole for counting, we've got formulas for reading recipes, and we have mass percent as a fingerprint. So now, let's put it all together. It's time to play detective and solve a molecular mystery. So here's our case. Some lab technicians have analyzed this unknown substance. All they know is that it contains 3 elements: carbon, hydrogen, and oxygen. The big question is, what is it? And here's the evidence they found. They ran the tests and got its mass composition. It's about 40% carbon, a little under 7% hydrogen, and about 53% oxygen. So, how in the world do we get from these percentages to an actual chemical formula? This is where our toolkit shines. First, we just pretend we have a 100-gram sample. It's a neat trick that lets us just change the percent signs to grams. Then, just like we did with copper, We use the molar mass for each element to convert those grams into moles. Now, that gives us the ratio of moles, but the numbers are kind of messy. So to clean it up, we just divide all of them by whichever one is the smallest. And that scales everything down to the simplest possible whole number ratio. And what we get is a ratio of 1 to 2 to 1. So our formula is CH2O. Now, this is called the empirical formula. It's the simplest ratio of atoms in that compound, 1 carbon for every 2 hydrogens and 1 oxygen. But hang on a second. Are we done? Is the case closed? Not quite, because the simplest ratio isn't always the actual, true formula of the molecule. We're missing one last piece of the puzzle. The true identity of a molecule is called its molecular formula. This is the actual number of atoms. And the cool thing is, it's always a simple whole number multiple of that empirical formula we just figured out. To find that multiplier, we need one final clue from the lab, the compound's actual molar mass. And they told us it's 60 grams per mole. So now we just compare that to the mass of our simple formula, CH2O, which adds up to 30. Well, 60 divided by 30 is 2. So the real molecule is exactly twice as heavy as our simplest version. Our multiplier is 2. We just multiply everything in our empirical formula by 2, and voila! Case solved. The true identity of our unknown substance is C2H4O2, and you might know this stuff as acetic acid. It's the main ingredient in vinegar. So let's just recap the awesome set of tools you have now. You know how to use the mole to count atoms just by weighing them. You can read chemical formulas like atomic recipes. You can find a compound's unique fingerprint using its mass percent. And you have a step-by-step method to put it all together and figure out a molecule's true identity. You know, this toolkit isn't just for solving little puzzles like this. This is the fundamental logic that gets used in forensics labs, in developing life-saving new medicines, and in creating the advanced materials that are literally shaping our modern world. We've just unlocked one chemical formula, but now you have the master keys. So the only question left is, what other mysteries are you going to unlock?